For over a century, transportation has relied on a system that burns fuel to create controlled explosions. But this mechanical process comes with a severe structural flaw. Internal combustion engines waste between 70 and 80% of the energy they consume, losing it entirely to heat and mechanical friction. This data visualization shows the core contrast of the electric vehicle architecture. On the left, you see the internal combustion engine capturing only 20 to 30% of its potential energy. On the right, the electric motor operates at an 85 to 95% efficiency rate. This drastic improvement happens because the system entirely removes mechanical combustion from the equation. Instead of relying on expanding gases to push metal cylinders, it uses direct electromagnetic force. It is tempting to think of an EV as a traditional car that simply swapped a gas tank for a battery. That gets the science wrong. This is a completely different physics model for generating kinetic force. Because the moving parts do not physically grind against each other, the propulsion method is virtually frictionless. The energy transfer is clean, precise, and immediate. The real shift in modern transportation lies not in changing the type of fuel we consume, but in eliminating mechanical waste to achieve near-perfect energy conversion. To understand how this conversion works in practice, we have to audit the precise physical flow of an electron through the vehicle's internal systems. This blueprint outlines the 3 physical zones of an EV. It begins at the intake stage, where the vehicle draws raw power from the local electrical grid through the charging port. From there, the energy travels to the second stage, chemical storage. This occurs in the battery pack, which spans the entire floorboard of the chassis to maximize surface area and capacity. Finally, the energy reaches the third stage, where the stored power is converted into kinetic force within the drivetrain and electric motor on the axles. Mastering the EV architecture means tracking this specific, unbroken chain, from grid intake into electrochemistry, and finally into electromagnetism. The physical journey of that energy begins outside the car, where it must be extracted from the local power grid. Most residential and public chargers operate at level 1 or level 2. Here, the vehicle draws standard alternating current from the grid. This schematic illustrates a structural problem. Vehicle batteries cannot store AC power. To hold the energy, the electricity must flow through an internal component called the onboard charger, which converts the alternating current into direct current, or DC. This internal conversion acts as a physical bottleneck. The size and thermal limits of the onboard hardware dictate how fast the car can charge. Level 3 DC fast charging bypasses this limitation entirely by relying on massive external infrastructure. Here, you can see how Level 3 stations perform the AC to DC conversion outside the vehicle. By doing this, up to 500 kilowatts of raw DC power is pumped directly into the battery pack, completely bypassing the onboard charger. Bypassing this hardware allows the battery to reach an 80% charge in 30 minutes. However, pushing that much raw energy so quickly forces massive thermal strain on the battery itself, pushing the system against its most severe physical limitation. That massive thermal strain requires us to look directly inside the large battery pack arrayed across the floor of the vehicle. At this stage, the electrical energy is stored chemically. Today, most modern EVs rely on specific lithium-ion configurations, typically utilizing chemical combinations like nickel-manganese-cobalt or lithium iron phosphate. This cross-section breaks down a single lithium-ion cell, consisting of an anode, a cathode, and a liquid electrolyte separating them. During charging, lithium ions physically move across that liquid layer to store electrical energy. But this liquid medium creates a strict engineering ceiling. The liquid takes up too much physical volume inside the cell, capping the maximum energy density the battery can achieve. Furthermore, when subjected to the intense heat generated by DC fast charging, this liquid electrolyte becomes highly volatile. If the heat cannot dissipate, it risks triggering a chain reaction known as thermal runaway, where the cell rapidly overheats and degrades. Because of its physical volume and its volatility under heat, the liquid acts as a bottleneck, physically restricting range, limiting charging speed, and compromising structural safety. The engineering solution to this bottleneck is conceptually simple: remove the liquid entirely. This diagram illustrates a solid-state battery cell. The volatile liquid is replaced by a stable, solid conductive block allowing ions to pass. This shift increases energy density by up to 40%, while simultaneously shrinking the cell's physical footprint. Solid-state architecture eliminates the risk of thermal runaway and maximizes density, rewriting the physical rules of energy storage. Once that stored DC power is needed for motion, it must be inverted back into alternating current to physically drive the wheels. This current flows into the mechanical heart of the EV drivetrain, the Permanent Magnet Synchronous Motor. This cross-section details the two main components of the motor, the stationary stator and the inner spinning rotor. When current flows into the stator coils, it generates a rapidly rotating magnetic wave that locks onto the rotor's magnets, dragging it into a seamless high-speed spin. Because this torque is generated entirely by magnetic fields, without any parts physically rubbing together, the motor operates at over 90. The momentum generates fresh electricity inside the stator, which flows backward to recharge the battery. By converting kinetic momentum back into stored electricity, regenerative braking turns what traditional cars waste as frictional heat into a closed-loop energy recycling architecture. When you scale this internal efficiency up to a macro level, it forces us to rethink urban infrastructure. Because of its massive, highly efficient battery pack, an electric vehicle serves as a mobile energy storage node on the wider electrical grid. This capacity enables vehicle-to-grid, or V2G, technology, which allows the energy loop to flow bidirectionally. This diagram demonstrates how V2G integration works. Vehicles absorb excess solar or wind energy during the day when production is high, and then discharge it back into homes or the city during peak nighttime demand. By absorbing and releasing power on demand, V2G establishes the electric vehicle as a critical infrastructure tool required to stabilize intermittent renewable energy grids. But this brings us to the central paradox of electric mobility. Zero tailpipe emissions do not equal zero environmental impact. To calculate the actual footprint of an EV, policymakers rely on a rigorous framework called the well-to-wheel life cycle audit. This Sankey flowchart tracks the greenhouse gas emissions associated with a vehicle's entire lifespan. It reveals the heavy environmental toll of the extraction phase, specifically the mining of lithium and cobalt required to build the initial battery pack. Once the vehicle is on the road, its operational cleanliness is entirely dependent on the specific energy mix of the grid it plugs into. If the vehicle plugs into a coal-heavy grid, the operational emissions widen. If it draws from solar or wind, those emissions drop to near zero. The ultimate objective is to achieve a clean loop across the entire supply chain, from raw resource extraction to renewable charging infrastructure. The internal 95% efficiency of the electric vehicle sets a new ceiling for mechanical design, but its actual climate impact is bound to the grid we build to support it.